we're going to look at 4 of the types of reactions, and our goal is not to be able to predict the products, but instead, if you're given a chemical equation, to be able to classify it as one of the 4 types of reactions. So let's look over the 4 types in general, and then we will take a look on the next slide and see if we can classify them. So the first one I have up here is combination. And when I think of combination, just looking at the word combination, I see the word combine. And this is exactly what we're going to look for in this reaction. So we'll have reactants. See how they're separate here? There's A and B. And there could be more than just 2, but you have separate reactants, and they come together to form one product. So they combine. They come together. The second type of reaction that we have on this page is the decomposition. So when I think of decomposition, I think of the word decompose. And if something decomposes, it breaks down. And so when I think of this, when I look at this reaction, it's really the opposite of what's happening in combination, where they're coming together. In decomposition, you have one reactant, and it's breaking down. So then when you look on the product side, it has multiple separate things. So it's decomposition, or breaking down. Oftentimes, decomposition reactions require heat to get them to work. Now, we also then have a number 3, which is single replacement. So I notice this word single, which would mean one. In single replacement and double replacement, the next two, I like to think of dancing. So in single replacement, what you're going to keep in mind is this word single. So what happens is, I'm going to put here 1. So looking at this, so here if you notice reactant A is all by itself, and B and C are together. So A is single. And it's like you have a B and C are partners and they're dancing, and A then cuts in. So now look on the other side. Now a different one is single. B now is all by itself. It's standing against the wall, while A is dancing with C. So single replacement. On both sides of the equation, you'll have an element that's all by itself. And then also with it will be something that are like partners, 2 things together. And so they'll switch. Another way I think of it is A cuts in, kicking B out. Now then, double replacement is the last example. And so let's focus on the word double. So if you have double replacement, what double means to you is 2. So I'm going to think of 2. And in double replacement here, they switch partners. So again, I like to think about this in terms of dancing. So you have couple A dancing, and here it's represented by AB. And couple C, and then the second couple C, D dancing, and they switch. So if we look on the other side, A now, A is going to be with D. See here, AD. And then C is going to be with B. They switch partners. And it will always be the 2 outside partners are a new couple, and the 2 inside ones are a new couple. Now you may ask yourself, well, why did you not write AD and then BC? Well, these are ionic compounds. You'll see when we had the formula. So remember, when they're ionic, this is a plus and this is a minus. The first one's always the cation. So C is a plus and D is a minus. So when they switch partners, A is going to have to go all the way over here to find a new partner, D, and then C will have to go to find B, and so C is written first because it's positive. So if you think about that, it has to do with the charges and how we write the formulas. So let's look here. Here's some examples, and we'll do both of these problems together. If you want to pause here and try, the objective is I've given you a list 4 different reactions, and for you to classify them as one of the 4, combination, decomposition, single replacement, or double replacement. If you want to pause now and try to answer these first before I give you the answers, that's a good idea. So letter A, what I notice is I have copper and sulfur separate, and then they come together to form one thing, so they're combining, so this is a combination. I'm just writing C for combination. Letter B, I notice that the copper and the carbonate are all together, and then when I look on the product side, I see I have gone from one thing in breaking into pieces. Now I have 2 things. So it's decomposing because it's breaking apart. So that's decomposition. Letter C, I have, here's 1 separated from 2, and they combine to make one thing. So they're combining, they're separate, and they combine, and this is composition. And then letter D, there's one thing on this side, and then it breaks down into 2 things, so that's decomposition. So this first example gives you some, first problem gives you some examples of what combination and decomposition look like. Combination is combining, decomposition is decomposing or breaking down. So the second example is going to give you the difference between single and double displacement. So when I look at this first one, my eye goes right here, magnesium's all by itself, it's single. And if I look on the other side, there's also single. So this is what happens in single. Magnesium's all by itself, and it will displace the nickel. And so now if we look, magnesium is now with the nickel, and the nickel is kicked out, and it's all by itself. So this is single replacement. Now the magnesium's a metal, so it has to kick out another metal. So that's how it works. A metal will kick out another metal. Now let's look at letter B. I have potassium and iodide. And looking now, tin is with iodide, so they've switched. So if I look, potassium went with nitrate. See, the 2 outside ones came together, and the tin went with the iodine. Now, I notice here that tin has 2 iodides, but that just has to do with the charge. Because that's, well, if you think back to chapter 3, how they get together has to do with their charge. So that's where they switch double partners. Okay, this one, I don't see in letter C, I don't see anything single. So let's see, if it was double, potassium would get together with chlorine, and that's what it does. And then hydrogen, switch on the inside, would get together with cyanide, and that's what it does. So that's double replacement. They both switched partners, the outside ones and the inside ones. Now here I see sodium's all by itself, so I'm suspicious that's an individual. Aluminum's all by itself, that's individual. So look what's happened, sodium kicks out aluminum. So now sodium is in with the sulfate we see here, and aluminum's by itself. So that's single replacement. So remember, in single replacement you will have an element that's individual on both sides. So you'll have a single one on the reactant side, and it will kick out one, and then that one will be single on the product side. In double replacement, there's nobody that's single, and if you look at it carefully, the 2 partners have switched. So the outside 2 have gotten together, and now the inside 2 have gotten together. And just recall, and the order of those is based on their charges.